Hi, you're with Christian from AMC and we're talking today about Module 1 in Engineering Calculations. So from the outset, I just want to say that some students struggle with the concept of maths, some maths problems, and I just want to say that if you're one of those, if you're a student that struggles with maths, then please don't panic. This just means we're going to take a little bit more work to get there. So look, I just want to say too from the onset that, look, if you're confident with your maths skills, then feel free to skip this section. There's plenty of guidance in your workbook for you to go through the self-paced examples and then to complete the assessments. Now, with some of the self-paced examples, I can supply you with solutions. So what I want to say is if you're struggling at all, please don't be anxious. I can provide you with as much support as you need to get through this section. Just be in contact with me and we can work through and find solutions.
So let's cover just the basics on fractions. So we all know that 1/4, that represents 1 divided by 4. And we also know that that equals 0.25. So that's a real basic example, but I'm just going to demonstrate that for you on the calculator. So the way we go about it is simply 1 divided by 4, right? And I can just bring that into view on the screen. Then when I hit the equals button, and 0.25 is the answer. Okay, now I'll just go to a number that's a little bit more complicated. So I'm going to go 21 divided by 36. And type that in on the calculator, hit the equals, and we get 0.853333. I'll just write that up on here, 0.583333. I'll put that dot on, that means recurring, it just continues. All right, now we're going to have a look at how we express this as not such a long number. We have our decimal place. We know that this is less than 1. It's around a half, 0.5, a little bit over half. So what I want to do is represent this number without so many numbers to 2 decimal places. So I'm going to move, what I want to do is look at having only 2 numbers beyond my decimal place. And what we do in this instance, this is my first and my second number after the decimal place. And we're going to determine what this number is going to be. Now, to do that, we need to look at the number after our second decimal place. And if this number is between 1 and 4, then we round it down. And if it's between 5 and 9, then we round it up. So in this case, our number is between 1 and 4. So the number gets rounded down, and our answer, rounded to 2 decimal places, becomes 0.58. All right, I'm just going to have another look at a number that we're going to have to round up. So let me give you an example, 21.677312. All right, so we want to round this one to 2 decimal places. So I look at my second number after my decimal place, and then we investigate the number after that. So 7 is between the 5 and the 9, so we round this number up. So my number rounded to 2 decimal places now becomes 21.68. Because I had to round it up, I go to the next number up, and that is my number there. So I'll do one more example. So to round this one to 2 decimal places, I look at the number after my second decimal place. It's between 1 and 4, I round it down. So the answer becomes 61.33.
Okay, so we're going to be covering percentages just as an introduction to extend on the fractions that we've covered already. Percentages we're using a fair bit on vessels for tank volumes, all sorts of areas. So I just want to go through the basics there. A percentage is, as it sounds, per cent, is part of a century, if you like. So everything's out of 100. If we look at it quite simply though, these badly drawn circles, we've got this, if it's whole, we have that as 1. we know that if we want to go 50%, try to get a line through the center, we know that that's half the circle on one side and half the other. So if we've got 50% of something shaded, there's our 50%. If we want to look at 30% in the shaded, we have that. I wrote that down as 0.3. What that actually is 100 divided by 100. It's a whole 100 out of 100, so that becomes 1. If we look at this one, it's 50 parts out of 100, which is equal to the 0.5. And the same thing on this third one, it would be 30 parts in 100. So we saw before 100% of something can be expressed mathematically as 100 divided by 100 equals 1. 50% is 50 over 100 equals 0.5, and so on. So 38% equals 38 divided by 100 equals 0.38. Looking at a smaller number, 7% equals 7 divided by 100. Put it into your calculator and you get 0.07. There's another way of doing that without a calculator if you, or if it's a number that's not divided straight into 100. We can look at 7.0, and what we do is we move across 2 decimal places. 1, 2, we're going to put a 0 in here, and when we finish up we've got to put a dot in front of, so 0.07, which is the same thing. We're looking at also numbers such as, say, 125% of a number, 125% of 4,500 litres. We want to look at that, and we want to find out, for instance, if we need a 25% fuel reserve, if we times it by 100%, that's timesing it by 1, so it ends up being itself. So what we can actually do to find out, say, a 25% reserve on top of 4,500 litres, we can go 1.25 multiplied by 4,500. Put this into the calculator. And we end up getting 5,625 litres. So that's a nice simple way. Instead of taking, people want to take 25% of it, which will be 1,625 litres, then add it onto the 4,500 to get that sum. That's the basics there. We can also look at percentages from the point of view of, if we look at a number here, 15 divided by 60 as a percent. For those who've done a bit of maths, you can see that 15 goes into 64 times, so that's actually equal to a quarter, which is 0.25 or 25%. Okay. So now if we want to take 20% of a number, we can either go 20 on 100 multiplied by 2,500 equals 500. So for litres there, if we need to get 20% of that number, and you can see there that that's 1/5 of 2,500 is 500. Some other examples, we might want to find out what is 19/64 as a percent. So as we said before, 19 divided by 64 equals, multiplied by 100 is 29.6875. Now looking at 29.6875, looking at rounding that down to 2 decimal places, here's a good example. I'll actually do it to 3 decimal places to start with. 29.68, we look at, for 3 decimal places it's a 5, so that becomes 8 to 3 decimal places. If we want to go 2 decimal places, 29.69, because that 8 is higher than 5, greater than 5. Obviously to 1 decimal place, then that becomes 29.7, and to a whole number that would round up to 30. So just showing how we do that as a backup. So moving on to algebra as a new topic. We use a little bit of algebra in our basic engineering calculations, so it's good to get a head start on how to do the very basics. So we don't, if you go onto a web page, you don't want to get too involved with rearranging simultaneous equations, things like that. We just want to go through the very basics, and the main thing we have to do is try to rearrange a formula. So looking at this one here, we use symbols, we can use whatever we want, but A equals B divided by C here. I just wanted to show some ways of getting you've got the numerator and the denominator, and we can move this equation around to rearrange to make, say, C the subject of the formula. What we say at the moment, A is the subject of the formula, A equals B divided by C. If we want to say that B equals 16 and C equals 8, then the solution to this, A is 16 divided by 8 equals 2. Now you notice how I work down the page with any of these things, similar to with the other examples, we work down the page. Therefore, our solution, A equals 2. We can see there, if we put these numbers back in, we see that 2 equals 16 divided by 8. Okay, so if we've had C is equal to 8, B is 16, we can write it down here. Our solution was A equals 2, so we can see here that 16 divided by 8 is actually 2. So in a similar way, I'd rather use this example here on how to rearrange that formula so you can see the numbers at work. What we can do is we can actually switch this subject of the formula with the denominator. We can actually switch those back straight across, and I can show you quite simply without doing any mathematics. If I've switched those two across, you can see here that 8 is in fact equal to 16 divided by 2. That's a correct statement. So you can see here that we can move the subject of the formula with the denominator back and forwards. I'll give you another example of that. I'll use that example that I used similar with the percentages before. So equally, we can switch these two around, and a correct statement is actually still the same thing. So 15 is in fact the same as, is equal to 60 divided by 4. So we're just seeing that we can switch the subject of the formula across to the numerator straight back and forwards. Now what I'm going to try to do is make B here the subject of the formula. So what we're doing, we can, a simple way that students often like is we can multiply both sides by whatever's on the denominator here, or A. So I'll just draw that in there. C times A equals B times A divided by A. So what we've done is, in fact, multiplied the left-hand side by A and the right-hand side by A. You'll see that from algebra that you've done, hopefully, A divided by A is in fact 1. So C times A is equal to B. Or B equals C times A. What we also do is just looking at introducing a number of things at once. In engineering, instead of putting the multiplication there, we can just have that dot, which means multiplied by. So that's rearranged the formula for B equals C times A. If I look at that from using numbers again, and I use an example of 160 divided by 2. If I want to make the numerator the subject of the formula, then 80 times 2, multiply the left hand side, because that was already over 2, we have to include that. And once again, that crosses out, so you can see here 160 equals 160. 80 times 2 equals 160. Just to apply that one. If I look at an example where we've got, I can make up whatever letters or numbers, etc. Just looking at, I'll get a new bit of paper. We'll look at, with algebra, a basic thing that people may come across in engineering. Voltage equals current times resistance, or V equals IR. Remembering that's multiplied there. Some people also see it as V equals A for current times R. But whatever we want to use, that's fine, depending on what your is. So if we know that the resistance is 4 ohms for R, we know our volts are 24 volts. What we have to do is rearrange this formula to find how much current, the I or the A, how much current is flowing through the circuit. So V equals I, I'll use the I. In this case, what we do, we can divide, if we want to make this the subject of the formula, we can divide both sides by R. Whatever you do on the left hand side, you have to do on the right hand side. We divide both sides by R, and we get R divided by R is 1. So current in effect is voltage divided by resistance. And after a while you get used to writing that out. So sorry about that. So if we're looking at this, putting those numbers in, voltage is 24 volts divided by the resistance of 4 ohms. So we know we have 6 amps flowing through the circuit. So there's lots of examples we can do with that. If we have it for another formula, just make up whatever I want to. P equals 16 S. If we want to find S as the subject of the formula, in this case, these are all multiplied, 16 times R times S. So what we've got to do is once again divide both sides by, if we want to make, we'll make S the subject of the formula. We divide both sides by whatever else is there. So 16R over 16R, that becomes 1. Therefore, that's my symbol for therefore. P over 16R equals S. We can obviously move that around so that these previous numbers, it's the same thing as a statement, having S is P divided by 16R. So So we've rearranged that formula. Okay, moving on to operations, it's quite important that we get the order correct, as I'll show you. I've put a basic little thing to try to remember here, BODMAS. So whether you'd remember the word BODMAS is another thing. But looking at the order that we do things, if we get to solve something like this, we have to look at doing it in the right order. If we don't do it in the right order, I'll show you some examples where we don't do it in the right order soon. But the basic rules, we do anything that's within the brackets first. So we can't add 7 to all that at the moment anyway. So the first thing we do in general is we work inside the brackets. Within this bracket, if we have a look through here, the first thing we've got to deal with is getting rid of this 5 squared. We need to get rid of this order of 2 here. 5 times 5 is 5 squared. So that's where we'll start. So 7 plus in the brackets, 6 times 5 squared is 5 times 5 plus 3. So we've got rid of that indice of 2, all the squared there. The next thing we've got to look at, if we go down the order, we've done the brackets first, the orders of the square roots, which we've got rid of, squares or square roots. Next thing we look at is multiplication or divisions. And within this bracket, we've got an addition and we've got a multiplication. So the next step is to get rid of that multiplication. 6 times 25, 150 plus 3. So you can see now we're just left with all additions, but we still have to solve whatever's in the brackets first. 7 plus 153 equals 160. I'll show you some other examples. If we look at now, this time it could be confusing for someone because we know you got to do multiplications before additions, but going back to the basic rules, we have a look at this. Do whatever's in the brackets first, no matter what. We haven't got any squares or square roots. We've got a division and addition. So the first thing we've got to do is get rid of these brackets. Okay, so 6 times 5 plus 3. Get that out of the way. 5 plus 3 is 8, equals 48. If we did it the wrong way, I don't like showing people the wrong way, but if I just give you an example of if we ignored those brackets and didn't do what's in the bracket first, we just decide we don't know what they mean, therefore we don't really care, it would become 6 times 5 is 30 plus 3 equals 33, which is clearly the wrong answer. So I'll do some other examples. Five times 2 squared, we've got a multiplication and we've got an indice or a square here. So what we have to do equals 5 times 2 times 2 equals 20. Okay. So you get the picture hopefully. If we look at one other, I'll just do a division in here. 30 divided by 5 times 3. Now in this case, we've got to do, if we have a look at all these here, we've got no bracket, we've got no squares, but we've got division and multiplication in the one line. Now what we have to do in this case is just work left to right. And the way this is drawn here isn't really helping us in some ways. A better way to draw it, to write it out, we can just go left to right, that's the rule. But if we show it another way here, 30 divided by 5, that's the same thing as what's written there, times 3. Now it becomes a little bit more obvious. We've got to get this into a whole number, then we can multiply. So we work from left across to right. 30 divided by 5 is 6 times 3 equals 18. So that gives you some examples of how to do things in that order. So remembering, always work what's inside the bracket. Get rid of your square roots or your squares, your cubes, etc. There could be 5 cubed, 5 times 5 times 5. I'll do that in a sec. Divisions and multiplications, then you do your additions and subtractions. If you can't decide, if it all seems to be all just positive, say additions and subtractions in a long line, do your normal work from left to right, and that will work out. If we're looking at moving on to another topic, another part of this with what's called indices, just introduced there before, say 8 squared equals 8 times 8 equals 64. Okay, so that's the squared is saying 8 times itself. We use that a fair bit. If we look at 8 cubed, 8 to the power of 3 here, that's in fact equal to 8 times 8 times 8. We go in here. We can do this a couple of ways. 8 cubed, we could just go 8 x to the 3 here. So we see the 512. 8 times 8 times 8, if you don't want to hit the button, gives us the same answer. But on the calculator, we've got this 8 cubed, we've got the, say x, whatever number we've put in, we cube it. If we want to do 8 squared, shows it there, equals 64. Same as what I did before. So the calculator can help us out if we're struggling with something like that. So 98 to the power of 3 to cube it. We don't have to put 98 times 98 times 98. I want you to understand what we're doing with a cube, but the calculator can help us there. So hopefully that's not too bad. We've also got a thing with indices. If we've got the number of 9,000, we use indices in engineering. We can say that that's the same as 9 times 10 to the 3. Similarly, nine times 10 to the 6 for 9 million. Because when we're dealing with stress and strain, we actually go even higher than in the millions. We deal with very large numbers. So instead of writing out the number all the time, we write that as 9 times 10 to the 6. And 10 to the 6, if you look, is, we'll start with this simpler one. 10 cubed is 10 times 10 times 10. Let's just try it. If we go 10 power of 3 is 1,000. So 9 times 1,000 is in fact 9,000. So you can see that in that case. 9 million, if we go 10 to the power. Now to the power of 6, we're going to have to, I'm just trying to find it on this calculator. Oops, that didn't work. There it is. So, sorry about that. 10 in this calculator, it's a bit different to my other one. With this one, we've always got to look for the x. See how we've got x squared here. What I had to do there was hit the number in 10 and then to the power of, I did this arrow up, which is to the power of, and I put my number of 6 in to get me 1 million. So once again, 9 times 10 to the 6 is 9 times a million, which is 9 million. So we use indices a fair bit with engineering. We've also got something called, if I use the number 81, and if we want to find the square root of that, we can say the square root of 81 equals 9. Square root of 81 equals 9, because 9 times 9 is that. So we can also write 81 to the power of 1/2, which is the same as the square root of. So while we're doing maths, we'll be seeing some things that are to the power of 1/2, which means the square root. So that's just another thing I wanted to mention. We can work with negative numbers. 9 times 10 to the minus 6 is going to be a very small number. At the moment, I just want to introduce these basics of the large numbers and some square roots, etc. Also got the cube root. The cube root of 81. I'm going to have to look at the, you see in here, I'll just see if the camera's got it very clear. You can see here we've got this little cube, there's a 3 with that square root sign. So what we have to do here is for any of these yellow functions on the calculator, we've got to hit shift, then we hit that button, and that gives us the cube root of 81. I can close those brackets or not, and that gives us 4.32. Once again, putting that back down to, say, 3 decimal places. So we've got the 6 here, so we have to go up to 7 because to 3 decimal places, 1, 2, 3. We're looking at that 7 being greater than 5 to 2 decimal places, so we just put to 2 to 3 decimal places there. If we want to make it to 2 decimal places, the 2 has a 7 behind it, so we have to make that into 1 decimal place once again. Because that was a 3, it drops down. So it's important that typically in our calculations as an answer, we go to around 2 decimal places of engineering. When we're doing calculations, we keep it to 5 or 6 decimal places because we sometimes multiply by some very large numbers. So now we're going to look at some areas of common shapes. When we're doing surface area, trying to calculate surface area of underwater, of a hull or a keel, we're working out tank volumes, we need to start with finding areas. That could just be trying to work out the amount of area on a deck or in a cockpit that we need to choose our paints. So we need to be able to work out areas of common shapes. To start with a rectangle, we've got the, just looking at the breadth B, we use B for the base or for the breadth, whatever you want to call it, and the H for height. Okay, you can see with this formula here, the area is base times height. So whatever that is in meters or centimeters, whatever, times the height, we can work that out. Now it's easiest to put everything in meters because then we work in everything in meters squared. Meters times meters is meters squared. So if we want to put in values, the height of this rectangle is 2.8 and the base width or the breadth is 4 meters, then the area is 4 times 2.8 equals 11.2 meters squared. I'd like to put, as when you do engineering, you're doing any sort of calculation, anything in a logbook or putting anything down, it's really good to put your final solution underlined because it makes it, it's your solution that you found, and for the next person that comes along, it makes sense to them what you've actually got, especially if you scribble on the page a lot. It's good to have that all sorted. So if we have a look at the triangle, I've used the same, the formula for a triangle is half base times the height. So basically, if we're looking at the area that we have here, you see it's similar to the rectangle, except it's actually half of that. And if we put the rectangle back in here, you can actually see that from the shaded area, that this area is the same area as that, and this area is the same area as that. So basically for a triangle, if we look at the what's called the perpendicular height at 90 degrees height, which is the same if we look at this rectangle as the height going up the side there. For the rectangle, the area was base times height, or the breadth times height, and in this case the formula is half of that, and you can see that quite clearly. That if I've drawn that a bit more accurately, you can see that quite clearly, that that is half of that area and that is half of that area. So the triangle's area is the perpendicular distance from the baseline there is yeah, we can see it there. So if we put that formula in, half breadth times height, you will see once again here I haven't even bothered to put the dot in here. With engineering we just go half BH. Okay, so that means multiplied by half times breadth times height. So you see it here, half times 4 times the height of 2.8, and the area is 5.6 meters squared. If we want to look at a circle, this is where it gets a bit trickier. We do lots of different things. Just starting at the basics, we do need to find, with any volume, we need to find the area first and times it by its length to get the volume, if it's parallel length. So looking at the area of a circle, a bit trickier because I can't draw circles. If we want to get this area, we can work that out. If it's a circle being hopefully a better shape than what I've done here, but the area is pi times radius squared. Just trying to keep it simple, pi r squared for that area. Now the trick is, if we do that with a compass, we can get that. We can have a 1.2 meter radius on a large compass or a string line, and we can draw that around from the center to get a what's called a diameter equals 2 times the radius equals 1.2 times 2 is 2.4 meters. Our diameter across, what we often check in fact is if we already have an existing circle shape, we measure from the widest point across to the widest point, and that will get us our diameter. So in fact that's where we often start, and there is a formula for that, but just keeping it simple. If we get the diameter, so let's say I'll do another circle, bad circle again. So this time we measure across and we find that the circle diameter was 0.8 of a meter. So the first thing we do, diameter equals 0.8 of a meter, therefore the radius equals half of that divided by 2, or 0.8 times 0.5 equals 0.4 of a meter. So the radius r is 0.4 of a meter. Putting that into the formula, the area of the circle, pi times r squared. Now if equals pi times 0.4 squared, looking at our order to do a calculation in, we've got to do the 0.4 first, 0.4 squared. So 0.4 x squared, you can see that. Now the tricky bit, not too tricky, but once again we're using the, if I move that up there, you can see, I'll move that in the light, there's the pi sitting there, that little yellow pi in this case. So what I've got to do, 4.2 times, got to hit shift, and then I've got to hit by 10. So you see the pi came up, and then I hit equals. So I've just taken that 4.8 and put it to 5 here. So that's our pure number that comes out. I've sort of shortened it down. It's only going to be so accurate. Once again, if I want to make that to say 3 decimal places, so it stops here, you'll see that I decimal places, DPs, I got to 503. We could also just say to 1 decimal place that equals 0.5. 0.5 of what? There's no point, we haven't answered the question yet because I've got to put the magic units in. If I don't put the units in, I've wasted my time because we don't really know then if you have an area of a tank end to get a volume and you don't put the units in, it could be in feet squared, centimetres squared. We have to put the units in, otherwise it doesn't make any sense to anyone afterwards or any sense to yourself when you go back to it. You can't make assumptions like that. So when it comes to doing your maths at the AMC, any wrong, if you don't put units in, basically you lose marks because it doesn't mean anything without the units. So that's good old circles. We can practice another one. Let's get that set up. So a circle diameter 1.9 meters. Circle has a diameter of 1.9 meters. Find the area. Okay, so the first thing is we write down what we have. The other thing we do is we write down the formula. So area equals pi times r squared. Now, to start with, we don't know the area. We know what pi is, 3.142. We know what we don't know the radius yet. So the first step we have to do, radius equals diameter divided by 2, 1.9 divided by 2 equals 0.95. So the area equals pi times 0.95 squared. Get it back on the calculator. We're going to do the squared first. Shift. So once again, just to get that clearer, hopefully 2.8353. If I round that 2.8 down to a 3. And if we want to do that to 2 decimal places, you see here we have to round that up to 4 because if we wanted to stop it at this 3 here, it's got a 5 after it, so we have to make that the 4. So the area of that circle is equal to 2.84. What have I done wrong? Have to put the units in to 2 decimal places. One other shape we use in the marine environment, we're looking at a shape called a trapezium. If you have a look at, I've sort of tried to draw in a bow of a vessel. There could be, say, a 4-peak tank up forward, and we're trying to work out the cross-sectional area of it. So it's got parallel tops and bottoms, and these side tanks, if you like, are on an angle. So we have to know the formula work out the formula for that. There is a formula. If we look at that, it's the top is the T plus the bottom divided by 2, and then multiply that by the height, the vertical height perpendicular to the base. So all we're actually doing here, if you look at this formula, all we're doing is finding the average of T and B. And I'll use a simple example of that. We have a trapezium that's 10 meters wide, using pretty simple numbers for myself, and 4 meters high. So 10 meters wide, 6 meters on the bottom. What we can see here, forgetting formulas and stuff, if you just want to try to remember and understand what we're doing here, if we want to get the average of these two numbers, the average is 10 plus 6 divided by 2 equals equals 8 meters. The average of those two. And we can see that quite clearly with this example. Another thing people like to do to show is this area here is the same as that area there, and likewise on here. So we can see that with that nice easy numbers that I chose. If that's to 6 meters and that's to 10, 8 is halfway between those, so the 8 meters would be the equivalent from here to here. So really the formula for it, I know that when people get back out to sea, they're not going to remember formulas, so if you get it as a concept, you get the average of the top and the bottom, or whatever sides are parallel, and then you multiply whatever value you get there by the height, and you get the area. So the area in this case, if I use the formula to put it in occasionally the correct way, that's meant to be a T, top plus bottom divided by 2 times the height. We worked that out before as 8 times 4 equals 32 meters squared. So that's that. We can, if it's we've got the units of meters squared, and we've got that basic cross-section area. So that's just a simple way of remembering that. We've got, moving on to volumes, just quickly, whenever we get, say if we have a tank that's a trapezoidal shape, and it's got parallel sides. I'll just use that example that we did before. Whenever, as long as these sides are parallel, whenever we try to get a volume of a tank, we can, it looks quite complex to try to find that, but whatever we have to do, we always find the area first and then multiply it by the length. So I'm going to use I'm just going to pluck some numbers out here. We've got a tank that's 8 meters wide at the top. We've got 6 meters at the bottom, using easy numbers. And the tank, if I look at the vertical distance of the tank, it's 4 meters. Okay, so that translates back to here, being 4 meters high. So if I get the average of 8 and 6, so if we look at the formula, the top plus the bottom divided by 2 multiplied by the height equals okay, so I found the area of 28 meters squared. So to find the volume now of that, all I've got to do, what information am I needing? I haven't got the length of the tank, so I'm going to say the tank is 12 meters long. The volume is, with any of these things, as long as it's parallel sided, whether it's a cylinder, a rectangular prison, this trapezoidal type tank, the volume equals the area, the cross-sectional area, multiplied by the length. So in this case, we've already got area is 28, the length is 12, so the volume equals 336. So therefore the volume equals 336 meters cubed. In this case, I have to use meters cubed because it's a volume, and if you look at it, this was area, which was meters times meters, became meters squared. We've now multiplied meters squared with another meter, so we have to keep that to meters cubed, because as you know, meters times meters becomes meters squared. We times that by meters and we get meters cubed. So we have to put that unit of meters cubed in. So that'll be the same with any of our volumes. If we look at quite a complex shape, we can look at a shape which is quite nasty, but if it had parallel, just to prove the point, I won't be able to draw that again now very well. If we had a parallel shape all the way along, it doesn't really matter what this cross-sectional area is. We can work that out for a number of ways. You could do it with calculus, you could do it by calculating little squares, centimetre squares up and how many full ones you get. But at the end of the day, we have to work out the cross-sectional area. We worked it out in at great length and found that it was 12 metres squared. The length of this tank, if the length of this structure or object, whatever we want to call it, is 15 metres long. So the volume equals area times length. Okay, equals 12 times 15. Put that in your calculator. 180 meters cubed. So I just wanted to prove that point. It doesn't really matter if we can work out any cross-sectional area, times it by its length, we find its volume.